Hello and welcome to the video. Today we're going to be going through a Bernoulli example. So this method is another substitution method that's often used for equations that are close to linear but not quite. If you remember, our linear equations usually look like we have some sort of y prime plus we have some function of x, usually denoted as p of x, y, and then equal to q of x. Normally this is our linear format where we have like a dy dx plus our p of x, and then our linear variable, and then q of x, so there's no y's on the side. So this would be linear and y, because we'll have a dy over dx here, and then we'll have a y here, so that's the linear variable. But in this case, we're almost linear, except we can't have anything in front of this, but we also have y's over here. And this is where Bernoulli's method comes into play. For Bernoulli's method, what we do is we take this term here on the end, which is usually just some y to a power or an x to a power, whatever variable you have that would be almost linear in. And then you want to make this substitution v equals to y of 1 minus n, where n is going to be the power right there. That'll be our n. So for this substitution in our equation, we want to substitute rv is equal to y of 1 minus 3. And then if we simplify this, we get v is equal to y to the negative second. And then we need to find a v prime to substitute in to our equation for this one. So in doing so, we then have a v prime is equal to a negative 2y to the negative 3. Then we'll have a y prime. The reason I did this is because both of these are functions of x, so therefore we need to have our y prime on the outside as well. After this, we want to simplify this a little bit more so we can get our dy dx by itself. So let's divide everything by x squared. And then cleaning this up, we will have a y prime plus a 3. And then we have an x on top and 2 on the bottom, so we'll have 1 on the bottom. And then y, and then we have that equals, we'll have a 4 over x squared y cubed. And if you notice here that we have, this is almost the same, we want to try and get this so we can substitute our v prime straight into this. So what I'm going to do is I'm going to divide by a negative 2 here. So I will have a negative 1/2 v prime equal to my y to the negative third, y to the first. And then once I have that, I'm going to divide everything by my y cubed. And the reason I divide by this is it helps simplify so I can make easy substitutions into the equation. Because if I do this, now I have, essentially if you flip this to the top, it'll be a y to the negative third, so we'll have y to the negative third y prime, plus we have a y on top, 3 on the bottom, so therefore we will have 2 on the bottom left. And if you flip that, so it would be the y squared on the bottom, and you flip it to the top, it'll become a negative exponent. So we'll have a 3 over x times a y to the negative second. And then this will be equal to 4 over x squared. And if you look, this helps us out a lot because our y to the negative second is just v. And then if we have our negative 1/2 v to the prime, it's just the y to the negative third y prime. So we can substitute these directly into our equation without any extra stuff. So doing that, we have a negative 1/2 v prime in place of this first term. Our second term, we have 3 over x still. And then we replace the y to the negative second with a v, and that is equal to 4 over x squared. If I rewrite this v prime to look a little more familiar as a dv over dx, where xv, 4 over x squared. Now once we have this, we are in fact almost ready to do our next substitution. So we need to multiply everything by a negative 1/2, because we want to get rid of this thing here, or actually, excuse me, not a negative 1/2, a negative 2, so that we can get rid of this negative 1/2 here. So if we distribute to everything, we will then have a dv over dx minus a 6 over xv, and that's equal to a negative 8 over x squared. And if you look, we are now linear in terms of v, which is great, because now we can do our integrating factor, which is the next step whenever we have a linear equation. So I'm going to set my integrating factor, it's often denoted as rho of x. I'm going to set that equal to, so we have e to the integral of p of x dx. This is our general form for an integrating factor. It'll never change. It'll always be the same. And in this case, our p of x is what's in front of our linear variable. Our linear variable is v, so I need to take this negative 6x and plug that in for my p of x. So I have e raised to the integral of a negative 6 over x dx. And if I pull out the negative 6, integral of 1 over x dx, this is just a basic integral, or we get natural log of x. So we'll have a negative 6 natural log of x, all raised to the e. And I want to move this negative 6 up to the top, because that's a logarithm rule. And then we can cancel the e and the natural log, which leaves us with x to the negative 6th is equal to rho of x. This is our simplified integrating factor. And now that we have that, we need to multiply our entire equation by this integrating factor. So if we do so, multiplying on both sides, so I will have an x to the negative 6th times my dv over dx minus 6 over xv, and that's equal to negative 8 over x squared. I'm going to rewrite this because this is a negative exponent, so therefore it's equal to 1 over x to the 6th. So if I do that, that'll make it easy to combine these two. So for the left-hand side, this will always become the derivative of two functions. The first function is your integrating factor. So I need to bring that down. So I'll have that as one of my functions. The second function is always your linear variable. So for us, that's v. And remember, it's the derivative of that. And then this will be equal to the simplified version over here. So I'm going to write it as negative 8x to the negative 8th. Because you just add the exponents, and then if I bring it back up, it becomes a negative exponent. And then at this point, I want to integrate, so I'm going to multiply by my dx to get that on the other side. And then if I integrate both sides here, my d and my integral will cancel on the left-hand side. So my d and the integral will cancel, which just leaves what's on the inside, which is what should always be the case. When next we want to pull out the negative 8 on the right-hand side. So we have an x to the negative 8th dx. So then we have x to the negative 6v equal to negative 8. And now this, we want to do the integral, so just reverse power rule. So if we add 1 to the exponent, we have x to the negative 7th. And we need to cancel, so we can just get a negative 8. So what I need to do is I need to multiply by a negative 1 over 7. And by doing that, I also need to add a constant. And don't forget, it can be on either side, doesn't matter which one you prefer. And then we have x to the negative 6th b is then equal to a positive 8 over 7 x to the negative 7th plus c. Then once we have that, I want to simplify this and get v by itself, so I'm going to divide by an x to the negative 6. So divide by x to the negative 6, divide by x to the negative 6. And then we have v is equal to, let's do 8 over 7. I'm going to reciprocate these, so it'll just be x to the 6th over x to the 7th. The reason I'm doing so is because a negative exponent just means, so this x to the negative 7th is equal to 1 over x to the 7th. And same for this, for the x to the negative 6th, it's just 1 over x to the 6th. So if I have a fraction divided by a fraction, you just multiply by the reciprocal, and therefore you'll end up with this. So now I can easily cancel these out, and I realize that I just have one x on the bottom. So I have v is equal to 8 over 7 times a 1 over x plus a c x to the 6th. Now I want to replace my v back in, so I have everything in terms of x and y's. And if we remember way back at the beginning, our v was equal to y to the negative 2nd. So by plugging that in, I have y to the negative 2nd equal to 8 over 7x plus c x to the 6th. And technically you could stop here at this example, or at this solution here. But if you want to get the explicit solution for y, alright, so if we wanted to simplify this further, what we can do is we can change our y to be 1 over y squared equal to 8 over 7x plus c x to the 6th. And then at this point we want to flip everything so that our y becomes on top. So I want y squared is equal to 7x over 8 plus a 1 over c x to the 6th. And then if I square root everything, I will have y is equal to the square root of 7x over 8 plus 1 over c x to the 6th. And then that would be our ultimate general solution.